All right, everyone. So here's what I want to do. I want to do a quick recap of acids and bases. And I think we need to start here because school year just ended really rapidly and quick, and half of us missed some of the acids, bases stuff. Half of us didn't. So if you feel like you were on top of the acids and bases stuff, great. This will be a simple review for you. But if not, this is going to be a great little review to help you get you started with everything that's happening. So let's dive straight in here. I want to go here. Boom. Nice. All right. So quick review of acids and bases. We talked about how acids and bases were dissolved in water, always dissolved in water. And so those solutions that were created when we dissolved them in water formed what we called electrolytes, things that conducted electricity. And so that was really important. And this word kept coming up, this idea of aqueous. So when we look at the forms that we knew before, the states of matter, we knew about solids, we knew about liquids, we knew about gases. But aqueous is that one extra step where aqueous are things that are dissolved in water. And in the cases of acids and bases, they create electrolytes, things that can conduct electricity. So as we throw back a little bit of history, Arrhenius was the first guy that suggested back in 1884 that acids and bases release specific ions. In the case of acids, Arrhenius suggested that acids were things that release hydrogen ions. And so it would look something like this, the ion H plus in water, and we put that little aqueous symbol to remind us that it was dissolved in water. And so the example we use all the time is this hydrogen chloride. So hydrogen chloride as an ionic compound looks like this, and for us we've got it in this gaseous state. So hydrogen chloride gas, when it gets dissolved in water, becomes aqueous, okay, dissolved in water, and it forms cations, hydrogen, and these chloride anions. Now, as soon as those hydrogen cations are present, we get an acid. And so that's why we use this example all the time. Hydrogen chloride as a gas, when it gets dissolved in water, becomes aqueous, and now we need to give that an acid name because it goes from just this gaseous form to an aqueous form, and so we call that hydrochloric acid or stomach acid. That's the example that we used as our classic example. This guy has a H plus ion present in there, and so that's why this guy becomes an acid. Now bases, Arrhenius proposed something very similar. Arrhenius said that bases are substances that when dissolved in water and become aqueous release hydroxide ions. And so this example here, we've got sodium hydroxide, that's the ionic compound name, as a solid, but as soon as we dissolve that in water, we get our sodium ion in an aqueous state, we get our hydroxide ion in an aqueous state, and that gives us the acid sodium hydroxide. And we know it's, a base, sodium hydroxide. We know it's a base because this hydroxide ion is present. So the classic example of that we used was this Drano. Drano is sodium hydroxide, it's in a powdered solid form, and as soon as we dissolve it in water, that's when we get sodium hydroxide as a base, and that becomes basic, and that's what helps clean out the drains in the situation of Drano. So we're going to go through in the next video a whole reminder on how to name, so stay tuned for that for the next video. But before that, I want to move on here, and I want to talk about, we needed a way to measure the relative concentrations of our acids and our bases. And so that's where this scale, the power of hydrogen scale, or the pH scale, and it measures the relative strength of an acid or a base by looking at the concentration of the hydrogen ions or the hydroxide ions. And so this scale went from 1 to 14, and we said that 7 was that perfect neutral, and anything less than 7 was acidic, anything more than 7 was basic or alkali. And so a pH of 1, our hydrochloric acid that we just talked about, pH of 2, that is more basic than a pH of 4, like tomato juice. Just like a pH of 12 is more basic than a pH of 10, hand soap. And so we use the scale, whether horizontally or vertically, to help us rank and figure out where they all fit in there. Now, a lot of you guys were away when we talked about it, but it's a worthwhile thing to recap on. We need to talk about how do we know, how do we compare the pH scale of acids and bases? And it's not as simple as just the gap. See, it's an exponential scale. And so we put up this example first. We said a pH of 1 is 100,000 times more concentrated, or 100,000 times stronger, or the other way we say it is in concentration, 1,000 times more hydrogen ions per liter, or 100,000, sorry, more hydrogen ions per liter than a pH of 6. And we had to do the math on that. So here's our math here. Here's a pH of 1 on our scale. Here's a pH of 6. If we were to count the jumps, 1, 2, 3, 4, 5, okay, this doesn't mean that a pH of 1 is 5 times stronger. It's in fact 1 times 10 to the power of 5. So 100,000. All right, the other way we could have done that is we could have said, okay, a pH of 6 minus a pH of 1, that gives us 5. That's what we put up here as our exponent, okay? So 1 times 10 to the power of 5 gives us 100,000. We could do the same thing with a base. We put up this slide and we said, okay, a pH of 11 has 1,000 times more hydroxide ions, or we could say is 1,000 times stronger than something with a pH of 8. Again, we could put it on the scale and show this. We count the jumps, 1, 2, 3, okay? And it's not 3 times stronger, but 10 to the power of 3. So it would be 1 times 10 to the power of 3. That gives us 1,000. So our pH of 8 is 1,000 times more basic, or sorry, more acidic than a pH of 11. You could say it the other way around too and say that a pH of 11 is 1,000 times more basic than a pH of 8. You could do it both ways, back and forth. All right, and so on a test, you would probably see one of these questions for sure. And we'll give you some practice at the end of this video. Finally, the last thing worth talking about is, okay, well, how do we tell if something is acidic or basic? How do we tell the acidity or alkalinity of a substance? And so really there's two things that we're talking about here. We're talking about qualitative means, what we see, and we're talking about quantitative means, what we can actually measure numbers wise. And so our qualitative measures would include things like litmus paper. With red litmus paper, it turns red in an acid, but it turns blue in a base. It can tell us whether it's basic or acidic. There's no number attached to it. It just tells us whether it's basic or acidic. So we've got various types of litmus paper. Red litmus paper turns blue with a base. Blue litmus paper turns red in the presence of an acid. Okay, but then we get into the quantitative ones, the ones that give us a number attached to it. And so there's two examples I want to show you here. The first one is pH paper. And this is paper, you tear it off the little strip here, you dip it in your substance, and then you hold it up to this scale, and it'll give you an approximate measure of the acidity or alkalinity of that particular substance. Even more accurate than that is this pH meter. And the pH meter is great because you dip the little probe in the substance and it'll give you an actual pH. So this substance has a pH of 3.78, which is an acidic substance. And so we can use both of these different types to get us close to, or in this case, an exact measurement of whether something is acidic or basic. I'm not going to talk about the specific indicators. You can go look at the slide deck for that for review. But that's it for this video. Give a try to some of those math ones where we're determining the relative strengths between different acids or bases. Give those a try and we'll pick it up in the next video with naming acids and bases.